Welcome to qnawire.
Hi, so for this problem, we're going to look at different Michael additions. So before we begin, let's quickly do a small review of the reaction mechanism. So the first step of the reaction mechanism is taking away one of the hydrogen of our Michael donor in order to generate a carbanion that is later going to attack a double bond on our Michael receptor. That double bond then is going to generate an enolate. This part over here is the enolate. And after we add some acid to our mixture and we start to heat up, we end up with our final product that is going to be with this double bond on the oxygen. So essentially what the question here is asking you is for A, C, E, and G, we want to arrive to the equivalent for this compound, and for B, D, F, and H, we want to arrive to the equivalent of this compound. Okay, that is going to be the final product of our Michael addition. So what we're going to do is we're going to quickly review what is going to happen in A, B, C, D, E, and F. And for G and H, I'm going to leave you for practicing that on your own because that is also important in order to learn how to do this. Okay? So let's start with the first compound that we have. I'm going to we have our Michael donor, that is this compound over here, and I'm going to show you a neat trick in order to know what is going to be the final product, okay, without writing down the whole reaction mechanism. You can always review the reaction mechanism if you require it, but whenever you have a Michael addition, what you need to bear in mind is that the hydrogen that is more acidic goes away and reacts with the acceptor. So, for example, in this case, what is going to happen is that we are going to end up with a negative charge on this hydrogen. This is going to attack our double bond. Okay, that double bond rearranges, and we end up with our enolate compound. So the result for A, it is going to be double bond oxygen, OET. Also, a thing that is almost always useful is to draw the products in a very similar way that you started with. So this compound over here, it is going to end up being our compound A. So we can copy that guy and paste it on this side. OET, oxygen, OET. Oh, sorry about that. Let's do it more with an angle. Double bond, oxygen minus. Okay. Now, if we want to go to the next step, what is going to happen is this compound, that is the answer for A, it is going to turn into the corresponding acid. Let me go down a little bit. And in order to get that acid, what is going to happen is that a pair of electrons recovers the carbonyl compound. The double bond is going to attack an H from the acid, and we're going to end up with our final Michael product. That is, we get rid of the double bond, and we recover the double bond with the oxygen. Here, if you want, you can add the hydrogen just for keeping the same structure that we have in the question. Same thing here, right? And same thing here. But in general, that is not necessary. We can omit those guys and everything is good. So these are going to be our compounds A and B. Okay, so let's write down. This is A and this is going to be B. Good. So for the next part, we have a different reaction, but the reaction mechanism is going to be exactly the same thing. Okay. Now the only thing that changes is that here I have CH3, oxygen, OET. Again, we're going to have the most acidic section, but now what we want to do is we're going to write our double bond oxygen, and in this case we have a CH3 on this side, right? And on the other side we have another CH3. So what is going to happen is that after we get rid of the acidic hydrogen on this position, in this case the reactant does that is the ethanoate, we get rid of that hydrogen, then we're able to attack on this position. Okay, and we can follow the same reaction mechanism. As you can see, after the attack on that position, the double bond goes away, forms a double bond on the other side. Actually, let me be more precise with the arrow because this can be confusing. You attack that carbon over there, the pair of electrons goes, and the product that we're going to find, in this case it's going to be product C, CH3. We're going to write down the same structure. Okay. Carbon, let's write it down in a very similar way. Double bond. And we're missing an extra carbon here. Okay. So this compound, it is going to be compound C, which after the addition of the acid, what is going to happen is that this part attacks an H plus from the environment. We end up with carbon, double bond oxygen. We write down the structure and then with a lot of care, double bond oxygen and a carbon additional here. So that is going to be our compound D. Okay. Now, for the next compound that we are going to have, we have a CN over here. You may be a little bit confused in this scenario because now we do not have the same Michael compound that we had before, like the same donor that we usually employ in these types of reactions. And the other complication that may arise is that now we are going to have a cyclic acceptor. But guess what? The thing is going to be exactly the same. The hydrogen on this position is going to be taken away by the ethanoate from the reaction conditions. So we end up here with a negative charge. That negative charge attacks the carbon. The pair of electrons comes here, and the oxygen gets a negative charge. Here, why we took away this hydrogen instead of the other one, because that is going to be the more acidic hydrogen that we have in that compound. Okay? So now what we get is going to be, I'm going to try to write the cycle as good as I can. So now this is going to be our compound E. Okay? And after the addition of acid and heat, the same thing as in the previous mechanisms. What happens is that the pair of electrons goes back and the pair for the double bond attacks an H plus from the environment. Normally this one is written as HB, but in this case, since you already have the H3O plus, and just to lighten up a little bit on the notation, and also considering that you're not asked about the reaction mechanism, just about the final product, this is going to be our final compound. We're going to get our cyclohexane. Sorry about that. That one looked a little bit funky. Carbon, our cyclohexane, and we double bond with the oxygen. Okay? And for the final compound, I'm going to leave it to you. Just a little bit of a hint because your professor in this case didn't want it to write things in the same way as in the previous problems. Just you need to realize that the donor is this compound that we have. And again, the same thing goes. The ethanoate takes away an hydrogen from this position, and your reactant, your acceptor for the donor, for the Michael addition, it is going to be, we have a double bond, which is in a cycle, and over here we have your aldehyde. Okay, so initially I was thinking about just leaving this one for you, but since we are already here, let's go ahead. The double bond gets here, and we generate the enolate. Okay, here, just to be careful, this one is not a double bond. Okay, so your product, it is going to be oxygen, double bond oxygen. Okay, we formed that carbon-carbon bond. We have our cyclohexane, and in this case, we're going to have, oops, our double bond in that position, double bond with the O minus in here. Okay, and that is going to be our compound G. Finally, same procedure as before, a pair of electrons from the oxygen forms the double bond. This pair of electrons is going to attack, let me put it on the other side just to not cramp things up. It's going to attack one of the H plus, and we end up with our final compound. Single bond, our cyclohexane in this position. In this carbon, one, and double bond oxygen. Okay, and over here we have a nitrogen, but we can always neglect it. And that is the final answer for H. And that would be all.